Okay, so good afternoon, everybody. My name is Beatrice Polacchi, and thank you for inviting me to give this talk, which will be about an experimental and theoretical work about verifiable multi-client distributed blind quantum computing on a Qline architecture. So first, I would like to introduce my group in Rome. This is the Quantum Lab. We work at Sapienza University of Rome, and I am currently a postdoc here. And the people we worked with to carry out this work, who are Mark, Elam, and Dominic from VeriCloud and Sorbonne. So our starting point is blind quantum computing with a single client, which is a protocol that, as we know now at this point, allows a user to delegate a complicated computation to a remote quantum server while keeping private all the data involved in the computation. So the input data, the algorithm itself, and the outcome, while having minimal quantum power on the client side, of course. So the idea, a bit more into the details of this protocol, is it takes two parties at this point, a client and a server. The computation is based on the measurement-based quantum computing model, so the server has a cluster state and needs to carry out a pattern of adaptive single qubit measurement on the cluster state, and these qubits are provided by the client, who is able to generate randomly prepared single qubits. And once the server receives these qubits that are that randomly prepared, it produces this big entangled state, and the second part is classical rounds of classical communication to update at each stage the next measurement basis for the cluster state. What we mean by verifiable blind quantum computing is simply that the client must put some dummy qubit into the cluster state in order to be able to detect the error rate that is that occurs during the computation at the server stage, and to be able to understand whether the server is behaving honestly or doing a good job. So this is a bit more into the details, just to understand also the classical rounds, how they work. The principle is that the client produces qubits in the, okay, this is the target computation. So our parameters are the x1 and x2, which are the input bits, and phi1 and phi2 are the measurement, the actual protocol to be carried out, the algorithm. In the blind version, the client prepares these plus qubits, rotated randomly around the z-axis, send them to the server, and the masking angle are measured according to this formula, which masks at the same time the theta angle, which masks the state, and the phi angle and the algorithm, and also the r bit, which masks the outcome of the computation, and the input bit xi is also kept secret. So, and each outcome will be corrected then according to the formula below. So our goal is to generalize in an experimental-friendly way this protocol that we have just seen. Why is it hard from the experimental point of view? Because when we take into account a group of clients who don't trust each other as we would like, they should compute that delta angle all together and taking into account all their secret parameters. So the secret parameters coming from each client must be taken into account the computation of the delta angle for each qubit. This would take into account classical functionalities such as secure multi-party computation, which would need a lot of more additional rounds of classical communication. And since we would like, as we saw also at the beginning of this workshop, to reduce the memory at this stage, quantum memories are not yet very still able to keep for a long time the quantum state. We would like to reduce this latency time. So what we did, our first proposal was we developed it from the theoretical and experimental point of view. So we thought about a scenario first with just 2 clients and 2 qubits, and the 2 clients are able to carry out this delegated computation together thanks to a third party. So all the rounds that would be needed in SMPC are carried out simply in the TTP party, which is the only trusted one, and therefore the round of classical communication becomes just 2, from the clients to the TTP and from the TTP to the server. And the TTP is the one that it's just a classical party that computes the delta angle with all the parameters from the clients. Then we also theoretically thought about an extended version with an arbitrary number of clients and of qubits, which is based on the Qline architecture. Also, in the small case, it is based on the Qline architecture, where untrusted source of qubits distribute qubits along the across the clients, who just rotate these qubits. So they do not need to prepare also the qubits. That is also happening here. And at the end of the line, each qubit goes to the server. So in this way, we are able to decrease the quantum power on the client side, but also to decrease the time latency on the server side, thanks to the TTP. So in this first version, we knew that there was an open question about verification with untrusted sources of qubits, because the clients are not completely aware of what they are rotating. They don't know what the sources is distributing to them. So thanks to the work of our favorite theorists, we could also demonstrate a verifiable version with some modifications to our setup. These modifications take into account another stage in the preparation part, which takes into account a bit flip of the state, not only rotations around the z-axis, and we perform both test and computation rounds. And what changes is the kind of measurements that the TTP asks the server to carry out on the test qubits. Yes. Since the idea is very similar to what we saw before, so the clients perform stabilizer operators, the outcome is deterministic, so they can basically know which is the error rate of the computation. We also took into account the hardware noise, and not only the server possible deviations from the correct and honest behavior. And thanks to this, we could individuate the maximum level of hardware noise that the clients should expect with the hardware they are using, and also the theoretical protocol security threshold, which is the sigma threshold. So we individuate a compromise, a trade-off between these two thresholds, and what we want is that our error rate is basically below the omega threshold for the clients to accept the protocol. This is our experimental setup. This is where I come into play. So in Rome, we built this setup, which is based, it is the small version, so we consider a 2-qubit, 2-client scenario. Sorry, 2-qubit, 3-client scenario. We use a Sagnac source of polarized polarization entangled photons, which are distributed to the clients with the fiber links. And each client has a set of half-wave plates or a liquid crystal with a half-wave plate to rotate the polarization, as I showed you before. So with bit flips and Z rotations. And at the end of the line, our server must measure 2 qubits in an adaptive way. So the first qubit is measured, and after this operation occurs, the second measurement basis will be adapted to the first measurement outcome. And this happens thanks to an electro-optical modulator, which is linked to this circuit, this fast circuit that receives in input the first two outcomes of the first measurements, and then gives a high voltage to the electro-optical modulator, which can switch fastly between two different measurement bases. And these are our results. So we both checked the performances of the protocol with 2 clients and 3 clients. Both the test rounds and the computational rounds in the experimental results agree quite well with the theoretical expectations, as you can see. And also we could see that the failure rate is below the omega threshold in both cases. So we showed that our protocol is secure and correct, but we also show that when the server is acting in a dishonest way, the failure rate is actually higher than the omega. So we are actually detecting that the server is behaving dishonestly. So I conclude here by doing a bit overview of this talk, where we saw how the Qline can be used as a versatile and modular linear quantum architecture for distributed blind quantum computing. We showed also how we can reduce the latency time on the server side by introducing just one trust assumption about the trusted third party. And also, we extended this protocol, both the verifiable and the non-verifiable one, to an arbitrary number of clients and qubits. And our latest results are also that we can verify this computation. So these are the works if you're interested, and I thank you very much for your attention.
We have time for one or two questions. Thank you for the great talk. I'm curious if you could mention specific, from the usage side, a specific application that could use this, that you think would use this type of distributed blind quantum computation.
But in principle, we saw until now, I would say, a lot of applications that would be possible. In the sense that, are you mentioning the architecture? Are you referring to the architecture?
I'm saying, suppose you're in front of industry people that are kind of figuring out how to use quantum. I don't know this crowd specifically, but and they're kind of saying, okay, how can we use this in our systems? What's the thing you will tell them that's kind of like, they cannot do this otherwise, but they can do this, or it's like orders of magnitude cheaper to do this instead of
Federated machine learning, privacy.
Yeah, exactly.
Okay. Can you help us understand why?
Because classically, if classically you want to do federated machine learning, again, if you want to have privacy, everybody wants to have privacy. What do you need to do? You need to bring FHE, etc., etc. You can do it. MBC, FHE, putting some, but this one is minimizing the assumption that you have. And you can, another way that imagine your data and your algorithm is quantum. So thank you, exactly. Don't do it classically. You need to run it on quantum computer, and everybody need to do it, this federated machine learning on several computer in a privacy preserving.
Yeah, for example, a bank who wants to take into account different data sets, but the data sets must be private. I don't know.
Do you have maybe it's a difficult question to answer, but do you have an idea of the delta between if you're doing this with FHE, for example, and if you're doing this with this? I know that this is experimental. Huh? This section is things that are still experimental, but what do you expect the delta to be maybe over time, or like what are we looking at in terms of the overhead difference in a way? And you can translate it in cost to some extent, but just if there's some notion of delta between classically doing computation on top of private data versus this.
I would pitch it that you need to think about, rather than the delta, thinking about how much you care about your data. If this data that you want to federate is like a healthcare data that you don't want to risk it somebody's leak, then you don't care about the cost. You might want not to do it with the lattice-based cryptography because it could be against the harvest and then attack. So if you want to really have this forward security, minimizing the assumption of the trust, and you're trying to do it with quantum, you cannot do it with FHE.
Yeah, this for quantum computers. And for QFHE, I don't know, Chris, what is the best overhead today, but probably orders of magnitude larger.
Then FHE.
No,
FHE adopted for quantum.
Ah, okay.
Yep.
Grazie per il talk. Can you go to the next slide? The test result. Yeah. So, are the experimental outcomes of the test correlated to how complicated the actual computation that the server must do? So, like, so basically, there in the server side, right? The server is doing some sort of computation, which in principle can be very easy or very complicated. Do we know if this influences the test round outcomes and the computational round outcomes? Like, if I run like a big ass computation, does that become worse or it stays the same?
I think that the security threshold would decrease, so we would be less robust in some way. And at the same time, of course, experimental noise would affect the test rounds, but we know that the clients can abort the protocol. So the important thing is that they can know whenever the computation is going bad or good.
Thank you.
Okay, great.